Thanks a lot. I hope the sound is okay. Yeah. All right. So, my name is Samit, and a very warm welcome to GreHack. And it's pretty chilly out here, so I hope the warm welcome helps you. My talk is going to be about OAuth. For those of you who are not aware, OAuth is an open standard for token-based delegated access. Put in simple terms, it means that if you are a resource owner, you can grant a third-party application access to the resources that you own using OAuth. So the talk is going to focus on the implementation pitfalls that we observe generally, very frequently, and it's going to focus on the attacks, and we're going to talk about how to mitigate against those attacks. So without further ado, let me just get to my intro. As Florent already mentioned, I work for the product security team at Citrix. Also, I lead the blue team. So basically my job is to make Citrix products a little more secure. And I am a web and mobile application security enthusiast, and I've spoken at a bunch of conferences, including InSec World, RomeHack, Security Fest, DEF CON China, Black Hat Asia, and AppSec US in the past. So the agenda for today is to cover OAuth, what is it and why do we need it. We're going to talk about access tokens and identity tokens, how they are different from each other and when they are used. Identity tokens is specifically used in OpenID Connect, but we're going to cover that as well. So, and we'll also touch upon the various grant types that OAuth has to offer. And we'll also look into how OAuth flow works for mobile applications. Finally, we'll come to the attacks and discuss the mitigation. And we'll end up with a short Q&A sessions. So why do we need OAuth in the first place? Let's try to understand this with the help of the scenario where you're logging into linkedin.com, you enter your LinkedIn credentials, and you see your dashboard. Now what if LinkedIn wants to access your Gmail contacts? Just to increase your contact list on LinkedIn. So in order to do so, you would have to give LinkedIn some sort of authorization to access your Gmail account's contacts. One way, and a very silly way of doing it, is to just give credentials to LinkedIn, and it goes ahead and logs into your Gmail account, gets your contact details, and just syncs it up with LinkedIn. So LinkedIn is your third-party application here. Gmail is your resource provider, and it is hosting your resources, which are the contacts, and you are the resource owner. So this is a very silly idea. You shouldn't be sharing your credentials with a third-party application. What are the problems that you see? Why is it a silly idea? Because the knowledge of your Gmail password allows LinkedIn to do far more than just fetch your contacts. It can log into your drive, scan your photographs, and do pretty much everything that you would do with your credentials. Also, access cannot be revoked from a single specific third-party application, because similarly, you would be sharing your credentials with multiple third-party. And if you want to revoke access from a single third-party, you will be doing that by changing your credentials. And if you change your credentials, the credential will change for all the third-party applications, not just one. So you can't revoke access from a specific third-party application. Another drawback is that LinkedIn would be required to store your credentials, and you shouldn't be trusting it with your Gmail credentials anyway, so that's a bad idea. And Google will be required to mandatorily support password-based authentication. So that's where OAuth came into being, and it's a protocol for delegating authorization supported by all platforms, web, desktop, and native apps. Native apps include mobile apps. So the advantages of OAuth is that the scope of access can be restricted to a specific third-party application. You can just allow access to your contacts only. So that's one specific advantage. And access granted can be revoked from a particular third-party application with OAuth. It avoids sharing of your credentials with the third party. That's a major win. And finally, it lays down a foundation for an authentication protocol which is also called OpenID Connect. So before we start discussing the flow of OAuth, I would like to introduce some of the entities that are involved in a typical OAuth flow. The first one is the resource owner himself. This is the end user who owns the resources. Then we have the client or the application or the relying party. All these three terms are synonymous and are used interchangeably. And this entity is basically the one which is requesting access to the end user's resource. And this was LinkedIn in our previous example. Then we have the resource server, which is the server which hosts the resources of the end user. This was Gmail in our case. Authorization server is the entity that is responsible for authenticating the user and prompting for authorization. And once the end user grants that authorization, the auth server is responsible for generating the access tokens and sending it back to the client or the application and the relying party. And this was Google in our case. Finally, the user agent. This is nothing but the browser. So we also need to understand that before the entire the OAuth flow starts, the authorization server also needs to know what all client applications are going to interact with it. And this is a mandatory step called client registration, which is required before proceeding with the OAuth flow. So what happens in this step is that the client tells the auth server that, see, I'm going to try and authenticate using your service. So here are my details. Just register me for your OAuth flow. So the client communicates application name, website, and the redirect URI to the auth server. The auth server generates the client ID and the client secret for the client. The auth server also stores the client ID and the redirect URI mapping with itself. And the redirect URI is basically used to send back access tokens to the client after when the client is actually trying to access the resource. So the redirect URI is used by the auth server to send back access tokens or authorization code. Finally, the client ID and the client secret is returned to the client. Now this client ID and secret is used for client authentication with the auth server. And we'll see where that happens in the entire flow. But this is a mandatory step required before we begin the OAuth flow. And of course, as the name suggests, the client secret is a confidential information and should be kept secret by the client itself. For those applications that cannot keep the client secret confidential, like a mobile application or a single page application, the client secret should never be used. And the reason for that is that mobile applications can be reverse engineered and the client secret can be figured out easily, or even you can intercept the traffic and find out what's the client secret. So whatever application is running at the end user's device cannot be trusted with the client secret, and the client secret should never be used with it. So let's just see how OAuth works in a nutshell. And I've listed down all the entities. There's the auth server here. Then we have the relying party or the client application here, which is Stack Exchange. Then we have the resource server and the end user here. So the end user visits Stack Exchange, and Stack Exchange shows this option of logging in with two different auth servers because it has previously registered with Google and Facebook as the auth server. So the client has registered with Google and Facebook. Let's say that the user chooses Google, and Stack Exchange will initiate an authorization request and redirect the user to the auth server, where the end user will be expected to log in. And after logging in, an authorization prompt will be shown to the end user, where Stack Exchange is trying to access some information of the end user. Would you like to grant it or not? And once the end user accepts this authorization prompt, an authorization code is generated and sent back at the client's redirect URI. That's where the redirect URI is actually used. The redirect URI is nothing but the URI of the client application. And once the client receives the auth code, it can hit the token endpoint at the auth server to get back an access token. And the access token again is sent back to the redirect URI. Now that the client has some form of authorization, which is basically in terms of the access token, it can then hit the resource server's endpoints using the token and fetch back the resources. So that's how a typical OAuth flow works. And the OpenID Connect flow is pretty much same in nature, except that in step 5, you will also see an identity token being generated in addition to the access token. Now the ID token is not used for authorization. It's an identity token and contains some information which convey the identity of the end user who has logged in. And this is consumed by the client application itself to populate the UI with the username and other user details. So the ID token is never sent to the resource server. In fact, the resource server doesn't need the ID token at all. The client consumes it. The auth server is generally opaque, and when I say opaque, you can't really make sense out of it. You cannot decode it to figure out any other information or infer information from it. It just conveys authorization and it is consumed by the resource server as we just discussed. Whereas the identity token is a JOT, and if you decode the JOT, you will get a lot of user details about the user who logged in. And as I mentioned before, it conveys the user's identity information like the user's name, email address, etc. And it is consumed by the client for displaying on the UI details about the user. So this brings us to the various grants that OAuth has to offer. There are primarily 4 different grants, of which the top 2 are the most famous ones, the authorization code grant and the implicit grant. These grants are used in different scenarios. I have a short diagram which explains in what scenario to use which one. But throughout the presentation, we'll be mostly talking about auth code grant flow and the implicit grant flow. So which grant to use when? Simply put, it's like if the application is the resource owner itself. So let's say that Facebook wants to fetch some resources that Facebook itself is owning, like the banner or some details or just the templates or whatever. So Facebook is trying to fetch its own resources. So that's where you go for the client credentials grant. And like in the previous example, where we had a third-party application called LinkedIn, and it was trying to access Google resources of the end user, that's where the authorization code grant is used. And this is the most famous one you'll see across websites. So if the application is absolutely trusted with user credentials, then you can go for resource owner password credential grant, which would mean that if we consider the previous situation, if you are willing to share your Google credentials with LinkedIn, then you can use this one, which is called resource owner password credentials grant. And finally, if the application is a mobile app or a single page application, you go for the authorization code grant along with something known as proof key for code exchange, which we'll discuss in detail later on. This is also abbreviated as PKCE. For single page applications, previously we could have used implicit grant as well, but of late, this technique has not been used in practice because it's vulnerable to a lot of attacks and it leaks the access tokens everywhere in your browser history and in the referer headers. So it's always good to use authorization code grant with PKCE for single page apps as well. So I'm a big fan of Marvel, and I made this small analogy with Avengers Infinity War. So the resource server will be played by the Soul Stone, and as you would know if you've seen the movie, the Red Skull owned or knew or had possession of the Soul Stone. So resource owner, which is Red Skull, has the Soul Stone. And then we have Thanos, who wanted access to the Soul Stone. And then we have Gamora, who knew where the Soul Stone is. It was on Vormir, and she could supervise access to it in a way. So she'll play the role of the auth server. So let's see how we just saw the flow in a nutshell. Now we'll discuss more details on it. So client or Thanos wants to access the soul stone or the resource. He hits the resource endpoint and he gets an unauthorized message because he doesn't still have any tokens with him, access tokens. So the client then redirects the end user to the authorization server, where the end user is going to authenticate and grant the authorization. And once the auth code is generated and sent back to the client, we know that the client will now exchange this for an access token at the token endpoint, get back the token, and finally hit the token and finally hit the resource endpoint with the token and get back the resource. So if you notice, the client credentials are also required in this step for authenticating the client with the auth server. Now this is where the client ID and client secret is sent to the auth server. So Thanos is happy, he gets the soul stone finally. And if you see the traffic on the wire, you're hitting, in the authorization request, you're hitting the auth endpoint on the auth server, along with some parameters in the request, which includes the redirect URI, the scope, and the state. So the redirect URI is nothing but the URI of the application or the client, and the scope tells the auth server what kind of details the client is trying to access. In this case, the client is trying to access photos of the user. And the state parameter is used to avoid CSRF attacks, and we'll see how later on. So in the response, you will see that the authorization code is returned and the state parameter is reflected back as it is. Then finally, when the token exchange step happens, the auth code is expected in the request parameter along with the client secret and the client ID, client credentials basically. And this is the token endpoint which is being hit. And as a response to it, you'll get back the access token. So what are the advantages of using the auth code grant flow? Number one, it provides the ability to authenticate the client, which is happening right here. Next, the access token never gets leaked into the browser's history or in the referrer header. That's because it comes in as a post response to the client itself, and it never goes through the user's browser. Now, this brings us to implicit grant, and if you see the entire flow, it is pretty much same except that there's no requirement of the authorization code. It never gets generated. Instead, when you're hitting the authorized endpoint, a token is generated and sent back to the client directly. And if you notice the traffic on the wire, you'll see that the authorization request looks pretty much same. In the response, there's no auth code. Instead, the access token is directly sent back to the application. Well, there are a few disadvantages of this. There's no client authentication involved, and the access token can end up in the browser's history because it's coming in as the response, it's in the redirect URS parameter. So it can end up in your browser's history, and it can also leak in referrer headers when you're redirecting to a different third-party application. So this brings us to OAuth for mobile clients, and the blueprint remains the same. The client initiates the auth request, end user authenticates and approves, server returns the control with the auth code is exchanged for an access token, and the protected APIs are invoked. But let's go through the details on how mobile applications are different from web applications when it comes to OAuth. So here I have the resource, which is the cloud API endpoints, and we have the auth server here. And this is the mobile application executing on the client device and the browser here. So once the client needs to access some resources, it will invoke the browser and redirect the browser to the authorized endpoint of the auth server, where the user will, of course, authenticate. And once the user authenticates, an authorization prompt will be shown to the end user on the native application. Once the user approves of this authorization, the auth code is generated by the auth server and sent to the browser. Now, this is where things get tricky because the browser needs to convey the auth code to the native application. And it needs to figure out which application should I send this auth code to. For that, we have something known as custom URI scheme. So every application can register a custom URI scheme on the operating system, which is nothing but a callback handling mechanism. So the browser, when it gets a URL starting with xcom mycorp myapp, it will know that this is the particular application that I need to convey the code to. So every application can register for certain custom URI schemes. And let's see how that happens. So in the manifest file on Android operating system, you can declare a scheme with xcom mycorp app. And whenever the browser sees any traffic coming in for this particular scheme, it will redirect it to the native application that registered for it. So once the native application gets the authorization code, it can then hit the token endpoint and get back the bearer token in response. That's the auth code there in the request and the client ID run type of the application. And finally, once the native application gets access to the access token, it can hit the endpoints or the resource endpoints with the token embedded in the authorization header. So we've talked a lot of theoretical stuff already, and time for some action. So we'll talk about some attacks and how they can be mitigated. We'll start with the authorization code intercept attack, and this specific attack is on mobile applications. And the precondition for this attack is that the client secret shouldn't be provisioned, and since it's a mobile application, we already know that client secret is not even provisioned for mobile apps or is useless. It can easily be figured out. That's one precondition. The other one is that the attacker should be able to install a malicious application on the mobile device of the end user. So here on the left hand side, on the end user's device, you have a legit app, and then you have the malicious application. And the third assumption is, and it's also possible, very possible, because the malicious application can register for the same custom URI scheme as that of the legitimate application. And there's nothing hindering that. So you see where this is going now, because when the authorization request is generated and the auth code is sent back to the browser now knows that there are two apps that have registered with the same custom URI scheme, and it will redirect the auth code to both of them. And now the malicious application can also exchange this auth code for an access token and get access to the user's resources. So how do we mitigate this attack? So there's something, you should not use custom URI schemes at all, because there's no naming authority and multiple apps can register for the same custom URI schemes. Instead, you should always use claimed HTTPS scheme URI redirection. Now what's that? With claimed HTTPS scheme, the scheme remains HTTPS followed by the FQDN of the application. Now every application, when it registers for this particular HTTPS scheme, it needs to prove that it owns the FQDN. So at any point of time, there cannot be more than one application that registers a particular FQDN URI. So basically the destination app is guaranteed by the operating system to the auth server. But still, if you're still using some legacy apps and you have a lot of custom URI schemes being used, then what you can do is use proof key for code exchange, also known as PKCE. And it adds on some elements to the typical OAuth flow. If you go through the RFC, you'll notice that there's a code verifier that needs to be generated by the client, which is nothing but an alphanumeric value, pseudo-random alphanumeric value. And the hash of the code verifier needs to be sent along the authorization request along with the hash method. So T_m is the hashing method, and T code verifier is the hashed value of the code verifier, also known as the code challenge. So once this hashed value reaches the server stores it as the code challenge value. And in the response, the authorization code is sent back to the client. And as we already know, using the auth code intercept attack, the malicious client can also get the authorization code. But in the next request to the token endpoint, the auth server expects the code verifier's value from the client. And once the code verifier reaches the server, it computes the hash again and matches it with the previously stored code challenge value. If they are equal, only then the access token is returned. So the malicious client can never get to know the code verifier's value because it has been generated by the client, the legitimate client. And therefore, even if the malicious client gets the auth code, it cannot make this request successfully and get the access token value because it doesn't know the code verifier value. Now this is known as PKCE, and I'm going to demo a vulnerability I found on Microsoft's identity provider, which was a faulty implementation of PKCE, and I'll talk you through that. So if you notice here, there are 3 endpoints I'm hitting. Number one is the login windows.net. This is the FQDN of the Microsoft's identity provider. And you'll notice that there's a login endpoint I'm hitting, there is an authorized endpoint I'm hitting, and then there's a token endpoint, as we've already seen in the OAuth flow. These are the endpoints that are hit. So if you notice in the request, you will observe that there's a code challenge value, which is the hashed value of the code verifier being sent in the authorized request. And there's a redirect URI, which is nothing but my mobile application's redirect URI. In the response, since the end user is not yet authenticated, I get redirected to the login endpoint. And once I log in, the authorization code is generated and sent back to the redirect URI that I initially mentioned. So this is the authorization code, and it is being sent back to the redirect URI of my mobile application. And in the next request to the token endpoint, you will notice that the code verifier's value is being sent to Microsoft's IDP along with the authorization code to get back the tokens, refresh tokens, identity tokens, and access token. So I put it in the repeater, and as you can see in the response, you will get all the tokens. Now the problem with Microsoft's identity provider was that even if you remove the code verifier's value, it was still responding back with valid tokens, refresh tokens, identity tokens, and access tokens. And since the authorization code is not one-time use, I could replay it as many times without the code verifier's value to get back as many refresh tokens and identity tokens as I want, and therefore have lifetime access to the end user's resources. And this Microsoft's identity provider was being used by probably like multiple mobile applications. So you could, if you leak one authorization code, you get lifetime access to the resources of that end user because of the access to the refresh tokens. If you read through the RFC for OAuth for native applications, you will notice that it mandates the use of PKCE for such mobile applications, and the auth servers should always support PKCE. So, so it was a big goof up by Microsoft, and which brings us to the second attack, which is called the cross-site request forgery. And you might find it very similar to login CSRF. This attack happens on the client redirect URI. And the attack results in the client to believe that it is accessing the legitimate user's resources, wherein in reality it is accessing the attacker's resources. So I've created a pictorial representation of the attack to understand it better. So let's say the malicious or the attacker publishes a malicious website and the end user visits this website, attacker.com. Now the malicious website needs to generate a forged authorization response, and in the response it needs to replace the code with the attacker's auth code. The attacker can initiate an authorization himself and replace the code with the attacker's auth code instead of the legitimate end user's code, because he can't figure out the end user's code, but he can always replace it with his own code. And now what will happen is that the client will think that this is the legitimate end user's auth code and try to redeem it at the token endpoint on the auth server and get back the access token which belongs to the attacker now. And when it fetches the resource will actually be the attacker's resource and not the end user's resource. So as a result, the client thinks it is accessing end user's resource, but in reality it is not. It's accessing the attacker's resource. So how do you mitigate this? Is simply by putting a CSRF token in the state parameter which goes in the auth request. And this is, since the auth request is generated by the client, it can never be known, the state parameter value can never be known to the malicious website. So the client generates it and expects it back in the auth response. And in the auth response, this is replayed as it is, so reflected as it is. So the malicious website can never get to know the state parameter's value, and as a result, if the state parameter is missing here, the client will get to know that something is fishy. Now this brings me to the most famous of all, I mean the most widely spread attacks that happen on OAuth, which is basically occurring because of client-side open redirects. And as a result of this attack, generally you end up losing or leaking your access tokens and authorization codes. So a few assumptions that I'll make here to make this attack more understandable, because it's a pretty complicated attack. So we'll be using the implicit grant, but this attack is also applicable to auth code grant flows. And in auth code grant flows, you'll be leaking the auth code instead of the access tokens, but in implicit grant, you'll be leaking the access token. Then I'm assuming here that the client has registered this particular URL with the auth server. Client some site example /cb ? So there's a wildcard at the end, and this wildcard will be misused by the attacker, and we'll see how. And the client supports open redirect at this particular endpoint with the help of a redirect to parameter. So basically, if you hit this endpoint, you will be redirected to example.com. So let's get to the attack now. So the attacker, before that, here's the client domain, client some site example, which it has registered with the auth server. And the server sits on server.somesiteexample. So the attacker publishes a malicious website, evil.example, and the victim visits that FQDN. Now, once the victim visits it, the malicious website generates an authorization request which contains the redirect URI, and it is the client's genuine redirect URI followed by the redirect to parameter with the attacker's domain in it, client evil example. So if you decode this URL, you will get client some site example /cb ? Redirect to client evil example. And once this request reaches the auth server, the server matches it with the pattern that was registered, and the pattern was exactly same, client some site example /cb ? And this pattern matches this particular value. So the auth server approves of the redirection and redirects the access token back to the client. And since the client has an open redirect exposed, it will redirect this particular access token back to client evil example. So as a URL fragment, you will get the access token, and the attacker can easily extract that value. So the only mitigation is to not expose open redirect at all, because you'll lose your access tokens and auth code anyway. So please don't do that. That's point you should always note. So next one is phishing using users' trust in the auth server. And there are a few steps that the attacker needs to take. He just needs to register a client, he just needs to register a domain which the attacker controls with the auth server. And then he misuses the trust that the end user has in the authorization server. So the auth server could be Google or Facebook, and once the attacker registers a particular redirect URI with Facebook or Google, he can just create this URL starting with authorization server's domain followed by the redirect URI of the attacker domain. And when the victim clicks on it, it will be redirected to the attacker's domain where the attacker can create a phishing page and extract whatever details it wants. So it's the responsibility of the authorization servers to inform the end user that it is going to redirect to a third-party application, which is this particular domain. And not always will you see that happening. Auth servers generally don't care about it. So easily the phishing attacks can happen because of the trust that the end user has in the auth servers. Now this one is interesting attack, and try to stay with me here because it gets a little complicated again. So this happens when the client application has registered with multiple authorization servers like Facebook, Google, etc. And one of the auth server turns malicious. And the intent of the malicious auth server is to get access tokens which are generated by the other legitimate auth servers which are not malicious. And the only precondition here is that the client has registered for the same redirect URI for all its auth servers. So even for Google it has the same redirect URI, even for Facebook it has the same redirect URI. And that's what causes the attack. So I have various entities listed here. We'll be assuming that the end user is trying to access resources from the same auth server. So I have Facebook and Facebook's resources, Google and Google's resources here. And the end user has resources on both the auth servers. And the client has registered with Google and as well as Facebook. So once the user, let's say, chooses Facebook as its auth server, LinkedIn will initiate an auth request to Facebook's auth server. And Facebook is malicious. So what it does is that once the request reaches Facebook, it will, instead of showing the prompt to the user itself, it will redirect to Google's authorization page, and Google will show you the authorization. So if the end user is not attentive enough to see that the authorization prompt is coming in from Google instead of Facebook, what will happen is that after approvals, the auth code will be generated by Google's auth server and sent back to LinkedIn. And LinkedIn knows that the authorization was started with Facebook, so it will try to redeem the auth code that Google generated at Facebook's endpoint. And Facebook will then redirect that auth token to Google's endpoint, and the token that they generated will be sent to LinkedIn, and LinkedIn, because it knows that Facebook is the one that we started the authentication authorization flow with, it will again try to redeem the token at Facebook's endpoint, Facebook's resource endpoint. So now Facebook has got the token, access token, that was generated by Google, and it can easily then access Google's resources on behalf of that user. So that's how the mix-up attack happens. And there's a simple fix to it. You should never use the same redirect URIs for different auth servers. You should always have different redirect URIs on the client exposed for different auth servers. And to show you how this works, how this fix works, the initial authorization request is to Facebook. And once the auth code is returned to the client's redirect URI, because it's Google redirecting, so it will be Google's redirect URI which will get the auth code. So the client will immediately notice that there's a discrepancy. The initial auth flow was started with Facebook and the redirect URI is of Google. And because of this discrepancy, the client will not then redeem the auth code at Facebook. So just to summarize, OAuth is used for delegating resource access to a third-party application, and access tokens prove authorization, and identity tokens prove authentication. For web apps, stick to authorization code grants, and for mobile applications, you could use auth code grant flow with PKCE. And then we also talked about how OAuth works on native applications and, of course, a bunch of attacks and the mitigations. And if you want to get started with OAuth and OpenID Connect, there are a bunch of references. These are good starting points. And of course, I'm there, so if you have some questions, then you can get back to me as well. And, okay. So, here are my contact details, just in case you want to drop me a message, and if you have some, we can have some good, interesting discussions. So thank you so much. That was it. Thank you for paying attention.
Thank you, Samit. So we got 3 minutes for questions. Maybe we can get more in case. So do you have any question for Samit? So I just one question, but apparently OAuth is pretty complex to implement. Do you know is there any work in terms of a formal verification of that protocol, and what were the output of it? That was for you.
Okay, so personally, I have only gone through the RFCs. So if you're talking about like probably mathematical formulations that have that verify the protocol itself, I doubt that exists, but there is a RFC committee obviously that sits and goes through and threat models the entire protocol flow. So that has been done throughout a long period of time, and there are various RFC pages which talks about what are recommended, what are the recommendations, and what are the best practices that you should always stick to. So as a pen tester, you should always be looking up for it, but yeah.
Okay. So no question? So thank you, Samit.
Thank you.
Oops. Premier fail de la journée.
Generally, communication are in HTTPS. So, how do you see the token exchange or the data exchange between the client and the server?
So, you're asking me that since the exchange is happening over TLS, how do you see the data, the traffic, right? Is that your question?
My question is that generally, communication between the client and the server are in HTTPS.
Yeah.
So it's encrypted.
Yeah.
So it may not be possible to get the token or the
Right.
Yeah.
So if you're talking about mobile clients, then you can still intercept the traffic between the client and the server, because mobile client is executing on the end user's mobile device. You can easily place a proxy in between and start intercepting, because you can install the certificates and start decrypting the traffic. So you'll have to install the proxies certificate on the mobile device so that you start decrypting the traffic. So that's possible. But if you're trying to intercept the traffic between a web application client and the auth server, that is not feasible, because it's a server-to-server call and the attacker can't intercept that.
Okay, thank you, Samit.